This is the structure which we will fix ourselves to. Okay. And then we will solve a very basic question. If you have an array, then nobody is going to ask you that, hey, tell me how many elements are present in the array, because that is a nonsense question. Array has a default size. So whatever is the size, that will be the total number of elements until unless you have initialized them. But when you have a tree, then it can be a good question to ask that, hey, this is the root, and now count me the number of nodes present in this tree. So let's say you have a tree which is rooted at this node 5, and you have 6, 9, 1, 2, 3, 0, 1, 4, something like that. Somebody asks you that, hey, count the total number of nodes. How will you do that? So you cannot do this question just by using a for loop or just by using a simple traversal. In a linear data structure, what happens? You can travel from I equals to 0 to I equals to 1, I equals to 1 to I equals to 2. But in this case, that is not possible. So you will have to take refuge in recursion. Now, I told you, if you have to solve a problem of tree using recursion, then you have to break this tree into a root and a separate left subtree and a separate right subtree. You have to think like that. When you think like that, you will be able to come up with some kind of recurrence relation, what you would have learned in recursion, like how a function is dependent on other functions, and then you will be able to code it. So you might have learned it in recursion that using recursion, you can make multiple calls, right? And those multiple calls are here for the multiple edges that are coming out from every node. So think of it in this manner. This is a tree rooted at this root R. So let's say I have a function count of R. This count of R will tell me that how many nodes are present in the tree whose root is R. Now, definition of the function is very important. It returns me the number of nodes present in the tree, which is rooted at R. Then I can say this is equals to 1 plus count of the nodes, which is present in left subtree, which will be rooted at root left, plus count of the nodes, which is present in right tree, which will be rooted at R right. You know, this is also called as a subtree. This is also called as a subtree. The way you have a subarray, you have got subtree also. And for every tree or subtree, its representative is its root. Because you have to be at root, then only you can travel all the other nodes coming down from it. So I can say number of nodes present in this is equals to 1. Why 1? That 1 is for the contribution of this. 1 plus the number of nodes present in that, plus the number of nodes present in that. When you look at this equation is saying that if you have to find the number of nodes in the big structure, then you first have to find the number of nodes in smaller structures. You find the number of nodes in this, find the number of nodes in this, add 1 to it. That's how you get the number of nodes present in this. And what is this? This is purely a recursive equation, which you can code and get your job done. Now, tell me one thing, what is it which is very special about recursion? Or what is it where you miss out on edge cases in recursion? Base conditions, termination conditions, very good. Tell me, is this thing correct for all the values of root or all the subtrees? Does it make sense? So let's say you come here, you are just talking about this much of subtree. Here, if you have to count the number of nodes and you say it will be 1 plus count of root left plus count of root right, okay, then what will happen is count of root left means you will go to null because root left is null, and count of root right would also mean that you would go to null. Now, when you are going to null, then there will be some issues. What kind of issues? Let's say you come over here and you again make this call, you do 1 plus count of root left, then you will actually do null arrow left. And whenever you do null arrow something, you get null pointer exception because null is nothing. When you use arrow operator, you are trying to extract something from R. And if R is null, the computer will say, hey, it's illegal. It's null pointer exception. So this thing is not applicable if R is null. So I would say that, hey, this thing is applicable only if R is non-null. But if R is null, think about R being null. So let's say there is an empty tree. there is an empty tree, there are no nodes in it, it means that its root would be null. So if the root is null, then the number of nodes would be 0. So in that case, you should return simply 0. So this is your base case. And this is your regular case, which I can call as your recurrence relation. So these two things you have to plug in your function and then call that function for the root of your entire tree, and then your job will be done. So let's say there is a function count. This count returns an integer denoting the number of nodes present in the tree, which is rooted at R. So you pass a node star R over here. And now the first thing you should always write is your base case termination condition. So you should say, hey, if R is null, so you can either write R equals to null, or you can just write not of R. So if R is null, return 0. Otherwise, you can just return this expression, which is intending to say 1 plus count of nodes in root left plus count of nodes in root right. That's it, job done. So if you understand how this is fundamentally correct, just make a note of it on your piece of paper that no matter what tree question you have, you always have to think in terms of root, LST, RST. You always have to break your big tree into these three components, and you will always be able to solve it. Okay. Now I'll just give you a glimpse of how this code would run. For that, I would need an input. Let's say you have a tree that looks like this. 2, 3, 4, 5, 6, and let's say 7. Okay, cool. This is your tree, and you want to run this code on top of that tree. So you would first, let's say this is your main function here. From this main function, you would make a call to that tree for this node. So you would call count at that node, which is 2. I mean, you would not pass 2 here, you would pass the address of 2. If let's say the address of 2 is stored in R, you would pass R over here. So what will happen? You call count of 2. Now let's look at the code. This thing is not null. So this termination condition will not run. Rather, this thing will run. When it runs, then it means it will first make a call to this 3, because this 3 is root left. So you will call count of 3. And after that, you will call count of 4. Correct? Now, you might have learned how recursion works. The control comes from here to here. So now when you are at count of 3, this thing gets called for 3. Again, this condition is false. So you will come here. When you will come here, you will make a call to count of 3's left, which is 5. So you will call count of 5. And after that, you would also call count of 3 right, which is 6. Now from count of 3, you have come to count of 5, right? So you have come to count of 5. Again, this 5 is not null. So you will come here. You will return 1 plus, so you will call count of 5 left. What is 5 left? What do you see in 5 left? It's null. It's null, right? So you will call count of null, correct? And after that, you would call count of 5 right. 5 right is also null. So you will call null here. So what has happened is that so far, computer knows about this much. So far, your computer has taken control from here to here, here to here, and then here to here. Now, at count of null, this condition will be true because the root is null. So you will return 0 from here. So you will return 0 from here. Similarly, at this count of null also, you will return 0 from here. Now, think when count of 5 was called, then you had returned 1 plus this thing plus that thing. Now this thing is 0. That thing is also 0. So count of 5 will return 1 plus 0 plus 0. So count of 5 will return 1 plus 0 plus 0, which is 1. And it makes sense to return 1. Why? Because I had told you the responsibility of this function is that whatever is the tree rooted at R, it should tell me how many nodes are present in that. So the tree rooted at 5 is this much, and the number of nodes present in this much is 1. That is the reason it is returning 1. This is how recursion works. The control goes from top to bottom, and the returns happen from bottom to top, and then they kind of, get consolidated as they move upwards. Okay, so now you come at count of 3. Count of 5 was already done. So this count of 3 will call that count of 6 that I had written over here. Count of 6 again, according to this logic, will call count of 6 left, which is null, and count of 6 right, which is also null. So it will call count of null. Count of null. What would it return? At null, you always return 0. So you return a 0 and you return a 0. And now again, if you remember, at count of 6, you had promised to return 1 plus something plus something. Those two things are 0, 0. So you return 1 plus 0, which is 1. Again, it makes sense. Because when you say count of 6, then the number of nodes present in this subtree is 1, and that is what it has done. So every children is doing their job. Like 5 is doing its job to say that, hey, I got 1 child within me. 6 is saying I got 1 child within me. And then this 3 is saying that I got 1 plus 1 plus 1 child, which is 3 children within me. So if you take a look at count of 3, you had said you will return 1 plus number of children in left and number of children in right. Number of children in left is 1, number of children in right is 1. So you'll return 1 plus 1 plus 1, which is 3. And again, it is right, because here there are 3 nodes. Similarly, when count of 4 is called, you will first call count of 4 left, which is null, and then you will call count of 4 right, which is 7. At null, again, you will return 0. And at count of 7, again, you will make a call to count of 7 left and count of 7 right, which is count of null, you will return 0, you will return 0. And at this count of 7, you will return 1 plus 0, which is 1. And this count of 4 will again return 1 plus 0 plus 1, which is 2. And this count of 2 will return 1 plus 3 plus 2, which is 6. That's how things get returned.